And in order to do that, I do need to tell you a few more specific surfaces in S4. Yesterday I gave you one example. I'll draw the picture. Sorry, dorm checkout. Just remember, I already forgot. Remember the times though. I showed you one example where we constructed this broken surface diagram. So I have some sort of surface. It's actually immersed in S3 right now, and it intersects itself in 3 circles. And I turned this into a 2-sphere that is actually embedded in S4 by, at each one of these circles of intersection, I chose one of the 2 pieces to be deeper in the 4th dimension, right? So I indicate that by drawing this like it's broken, meaning this piece that looks like it's not there is actually just deeper in the 4th dimension and I can't see it anymore. So now it's embedded here, and I repeat this at all of these intersections. Okay, so that's not very smooth. And then okay. And then we figured out that this was distinct from a 2-sphere that's just smaller round. They're distinguished by like the triple coloring trait, just like the trefoil. Okay. But I do want to talk about like somehow an actual family of examples. And the canonical family of examples of 2 spheres in S4 are called Spun knots. This is Arden. What year do I think this is? I think this is the 1940s. Is that? I'm really bad at, like, how old is Arden? Is 1940s like a crazy guess?
So which Arden is this?
1940s. Yeah. Okay. And I'm going to use notation that he would not have used, but it's to keep it consistent with some later definitions that I'm going to give you. I'm going to write that this depends on a choice of a classical knot in S3, and the result is a 2-sphere in S4 that I'm going to call tau 0, rho 0, k. And so obviously he wouldn't have called it that because spin doesn't start with tau or rho, so that's like a weird name. But it is going to make sense later. Yeah?
Excuse me, Maggie, I have a question. What is Arden's first name? It's a sauce question.
Yeah, so it's Emil.
Emil?
Yeah.
Arden from community. Okay.
Okay,
All
yeah.
right.
That's right. We have what I'm going to do in order to get this sphere. So I want to think about this as a pair. S4 containing a sphere. Is to reduce the complexity of the problem. S4 is bad because it's 4-dimensional. So I want to temporarily think of S4 as the boundary of B5, which is worse because it's 5-dimensional, sorry to point out, but it is contractible. But this has the advantage, well, B5 is just B3 cross B2. And that's clearly better because those are smaller numbers. So that tells us that S4 is just B3 cross S1 union S2 cross B2. And I'm sure you all knew that because this is a standard exercise in Robson. If you didn't, like, that's fine. That's how you do that. So I'm going to write this as a union of some piece in my 2-sphere that is in the B3 cross S1 part, and some piece in my 2-sphere that's in the S2 cross D2 part. Okay. And just like I cut S4 into 2 pieces that somehow were like smaller in dimension, I'm going to similarly have this 2-sphere be decomposed into 2 very simple pieces. It's going to be an annulus and a 2 disks. Okay, and that union would be a 2-sphere. Good. And well, I need this one of these 2 things, if not both, to somehow depend on a choice of a knot in the classical dimension. I guess that makes more sense for the annulus. I don't know how to get disks that depend on a knot, but at least an annulus is a circle. That's promising. So what I'll do is take a tangle for K. So let's say K is the trefoil knot, right? Instead of thinking of it as a knot, I want to think of it as an arc sitting inside of a 3-ball, 2 endpoints. Usually I would write this as like K with a dot to mean that it's like cut open. And so now what I'll do is consider the annulus inside of B3 cross S1, that's just K tangle cross S1. So it sits in there really naturally, right? And the boundary of this annulus is two circles. It's the two circles traced out by these two endpoints. If I call these two endpoints N and S for the north and south pole, then it's just the boundary is north and south pole cross S1, so I can cap off with north and south pole cross D2. Okay, so this is a spun knot. These two spheres are really interesting. It's very easy to distinguish them from each other in the sense that kind of a simple classical exercise is that when we look at the complement of the spun knot, it has the same fundamental group, isomorphic fundamental group, as the complement to the original knot we started off with. So the knot fundamental group is a really good invariant, and that already gives us infinitely many very different two spheres in S4. And in fact, this example that I did give you is a spun knot. That's where I got this from. We can actually see the spin symmetry very explicitly in this picture. So here's an axis of symmetry. So this picture's sitting in S3, right? Even though it's a diagram of something in S4 projected to S3. And I've just drawn this like unknot here. And the complement of this unknot is a solid torus, D2 cross S1. So that's supposed to be the B3 cross S1, but projected down a direction. Okay. Look at each one of the disks in this D2 cross S1. This is like D2 cross point, which is really the projection of B3 cross point. Well, clearly this two sphere is like symmetric about rotation about this axis. And how does this disk that I've just drawn intersect the two sphere? It intersects it in a tangle diagram like that. So I have like literally a trefoil tangle here. Like I got this two sphere by just taking a trefoil tangle and spinning it. That's how I do that. So this is the spun trefoil. It's really hard to make an actually interesting example. It's like a big problem in this area, but I don't know how to phrase this as a concrete problem. Just think of more examples. So even though spins are interesting, this is like a very classical construction. We understand these really well. Yeah?
Sorry, this is a simple question. Is it clear that this doesn't depend on your choice of tangle for K, or that there's a unique choice or something?
Well, there is a unique choice of the symmetry. I mean, to get a tangle, I took a point on K, took a neighborhood of that point. If I took a different point on K, I could just sort of translate it around and give me a homeomorphism between the tangles.
Okay.
So I'll get equivalent two knots. Yeah, that's a good question though. Okay, so I can generalize this construction. And historically, this was done in like two different steps, and that's why there's two things here, tau and rho, but I'm going to combine them all into one because I got other stuff to do today. This is going to be a definition of both Zeeman from the 1960s and Ligerich, no, not him, Ligerland from the 1990s. So now I'm going to, instead of writing tau 0, rho 0, I'm going to have a K, a knot in S3, and I'm going to get a two sphere in S4 that is also going to depend on two integers. I'm going to write tau m rho n. Okay. And in English, I would say this is the m twist n rho, spun knot of K, spin of K. Sort of confused by like the tense of this word. Like sometimes they're spun knots because they already exist, so they've been spun in the past, but sometimes it's like a spin of K because you're going to do it. I don't know. So what is this? It's the exact same idea. I still want to use this decomposition. So I want to think of this two sphere. Okay? As being something simple sitting inside of the B3 times S1. union, something simple, inside of S2 cross D2. And in fact, the two simple things are the same. We're going to have an annulus in 2. And the two disks are going to be the same because I just don't think I can think of a good, simple example of 2 disks sitting inside of S2 cross D2 that isn't just like 0.2 points cross D2. That's beyond me. So I'm just going to write, again, the same thing. But I want to choose a different annulus inside of V3 cross S1 with the same boundary. I want my annulus to still depend on K, just like this one did, but I want it now to also depend on these 2 integers M and N. Okay. So I'm sort of, this is like all backwards logic. I'm reverse engineering. Really what I do is think, well, what is V3 cross S1? V3 cross S1 is V3 cross I with the ends glued together. Okay, that doesn't sound like a very deep statement, but there's actually like a lot of work here. V3 cross I with the ends glued together, a priori, like if we don't know anything, we might wonder, what if I don't choose the identity map here to glue the ends together? What if I choose a non-trivial automorphism with a 3-ball? So I'll just write V. And now maybe you know that if I have a homomorphism of the 3-ball, that's the identity on the boundary, then in fact it is isotopic to the identity map. That's not like an easy theorem. You know, that's the Smale conjecture proved by Hatcher, but it is true. There's no interesting gluing map here. But this isn't just a 3-ball with an interval in it. 3-ball times an annulus, times an interval. This isn't just a 3-ball times an interval. This is a 3-ball times an interval that contains an annulus. Yeah, or it contains something. Okay. And so specifically, I want to build an annulus just like before by taking a copy of K, tangled, inside of each of these 3 balls. So this is like K times I. And if I glued up by the identity map, I would get exactly what I started off with in the 0, 0 case. I would just get the tangle cross S1, right? But what if now I choose an automorphism of the ball containing that tangle, and I don't make it be the identity? And now I don't have the Smale conjecture, like there could be something non-trivial. So phi is a homomorphism of the pair B3 tangle to itself. Self-homomorphism. Rel boundary. Okay. I have to write that, but it's rel boundary. And I choose phi, and I'm going to get a perfectly good 2-sphere. So I'll get an annulus after I glue these together. I'll call this A. That depends on phi. I'll put this here, and this is a 2-sphere. Okay. So now I just need to tell you what is phi. Like, what could I choose for phi other than the identity map? And if I happen to be working with
Question, so it's probably well studied, and it's just Hatcher who hasn't well studied it, but what is the automorphism group of 3 ball? I actually thought that for you that there was a non-trivial. I mean, anything that's the identity on the boundary sphere will be isotopic.
That's right, it's all isotopic to the identity.
Right, so.
But the isotopic to the identity does not need to fix this tangle. Now I'm considering homomorphisms of this pair. I don't expect this to be isotopic to the identity relative to this tangle. Yeah, and so I'll give you an explicit example of some that are not isotopic to the identity relative to the tangle. If my knot happens to admit a lot of extra symmetry, there might be many choices of phi. And this is something that Liverland studies in his paper. But no matter what the knot is, there's a 2-parameter family of homomorphisms, hence the M and the N, that I can always define. Okay, so let me erase my plan for tomorrow, and I'll give you a 2-parameter family. So this is phi mn. Here's sort of a blown-up picture of the ball containing the tangle. Okay, so phi that depends on M and N is going to be supported, like not just the identity, in a neighborhood of a certain torus. Okay, so here's a torus that I can always find. I'm going to take first a cylinder that is just a boundary of a tubular neighborhood of this tangle in the interior of the ball. Okay, and I'm going to end the cylinder before I actually get to the boundary. So this is not properly embedded right now. These two circles are sitting in the interior of the ball. I'm going to cap off with another cylinder that's parallel to the boundary of the ball. Okay, so I bet a lot of you have seen something like this picture called like a swallow-follow torus. I followed the tangle and then I swallowed the boundary or something like that. Okay, and what I'll do is I'll consider the homeomorphism that is a Dane twist about some curve on this torus. So what that means is I fix everything that's far away from the torus. And, well, if I look at a little arc that pierces the torus once transversely, after I apply the homeomorphism, this arc needs to map to another arc with the same endpoints. But instead of just going straight through the torus, first I need to wrap some number of times about a meridian and a longitude of that torus. Okay, that's a perfectly good homeomorphism. I'm not going to write it out in coordinates. Okay, so I'm going to do M Dane twists about a meridian curve, like a curve like this. And there should be a sign, like a positive and a negative Dane twist, but I haven't oriented anything, and I would still somehow get it wrong. Or an and. I'm going to do N Dane twists about the longitude curve. So it's a 0 frame longitude, which I won't draw because that was long. Okay, so that's perfectly good homeomorphism, and now it depends, there's a 2-parameter family. So I'll get a 2-sphere that really depends on these numbers. And in the case that these are 0, I just get the Spun map, which is why I call it this. Okay.
And that's not how you talk to the identity.
Yeah, it's not. I mean,
really obvious.
Well, I mean, again, this is like maybe a backwards way of doing it, but I could construct this 2-sphere and then write down a representation of the fundamental group of its complement. From, like, there's a sort of natural Seifert-Van-Kampen decomposition here, and I could check that that group has very different properties. What?
Well, anyway.
Yeah, that group is certainly not the same as the complement, like the fundamental group of this complement, the knot group. I've added a lot of extra relations. The meridian, some finite power of it might be in the center of the group. So Zeeman and Litherland both study this in detail. The M twist N roll spin okay is almost never.
And this is what you said. So how are you going to prove that this is going to not true? You're going to map it?
Well, I'm not going to prove it.
Well,
I'll just tell you that it's not. Okay. I mean, like, I could compute the fundamental group of this complement. If this were isotopic to the identity map, then this 2-sphere would be isotopic to that 2-sphere, or at least topologically equivalent to that 2-sphere. So the complements are the same fundamental group, but they don't. They give like a formula for the fundamental group, like a presentation in both these papers. And yeah, so you can get it from that.
Which you answered my second question was what about this orbital sequence generate? I mean, do they generate the automorphism fixation?
In general, no. I mean, so if my knot has extra symmetries, there might be more automorphisms. But I think this is the only 2-parameter family, or the only family of homeomorphisms, ball containing a tangle, that I can define no matter what the tangle is. Yeah, so that's why it's a little bit natural. And these 2-spheres are really nice. So in these 2 papers, Zeeman and Litherland make the following observation, which I'm going to point out because it's kind of important. As long as I twist a non-zero number of times, then it's the case that tau m rho n of k is fibered. In the same sense as a classical knot, I mean, the complement fibers over S1. So now the fibers are 3 manifolds. And I can actually say explicitly what the fibers are. So the fibers are M-fold branched covers. So that's why I need M to be non-zero. I mean, it also shows up in the proof. Results don't even make sense if M were 0. That's bad. But M-fold branched covers of certain Dane surgery on the knot. Okay. And the nice thing is that if M and N happen to be co-prime, then in fact this branching is degenerate. There isn't any branching. It's just an actual cover. So in the case of Zeeman's paper, he's not allowing any rolls. He's just considering M twist, 0 roll, spun knot of K. And so for him, this Dane surgery is trivial. We're just looking at actual S3. I guess there's a puncture to have boundary. And taking some M-fold branch cover of S3. So Zeeman proves that the twist spun knots without any rolls are fiber, and their fibers are cyclic branch covers of knots. And that's really nice, and that's why twist spun knots show up in like every paper about surfaces and four manifolds, because they're easy to construct, and they bound nice things, and their complements are fibered, and like, what else could you want? But they're super not generic. And the same thing with roll spun knots, super not generic, which is a problem because how are you possibly going to disprove conjectures about knotted surfaces with non-generic examples, right? But I don't have a better suggestion. Okay. But yeah, so these are twisted roll spun knots. And before I tell you some open problems, I did want to give you one more example, because I did say that I would tell you about band diagrams, and even as I was saying it, I was like, is that a lie? But I thought maybe I should. So let me give you one more interesting example of a surface in S4 using a band diagram, which we talked about at the very end of last time. And it's kind of like a joke that this is an interesting surface, but it's kind of not. So let's remember, I mean, I'll tell you for the first time, what does it mean for a surface in S4 to be the unknot? And this came up in a talk yesterday, and I forget who was talking, but somebody said what an unknot is. Maybe, was it you? Did you say what an unknot is? What'd you say?
Oh.
Not good, sorry.
Bounding a disk.
That's a great definition. So when is a surface to be unknotted? Wow. When is a surface unknotted? I don't know how to explain that. When is a surface unknotted? If we have a genus G surface sitting inside of S4, then we say this is unknotted if sigma G is the boundary of a genus G handle body inside of S4. And this makes sure that unknots are unique up to genus. Okay. The problem is that these are all oriented surfaces, and I want to consider arbitrary surfaces. So when is a projective plane unknotted? Because that doesn't bound anything. So what am I going to do? I think there is some paper by Lawson, or Price or someone, where he proves that, well, he defines a projective plane being unknotted in terms of bounding some like weird singular three-dimensional objects in this form. I have no idea what that was. So instead, what about, so this is orientable. For non-orientable, I just have to give you a favorite surface and declare that to be the unknot. Okay, that's fine. I don't have to justify myself. So what do? Well, I did all this work to think about Morse functions. So let's get just a single projective plane. And I want my projective plane to feel unknotted. I want it to be as simple as possible. So I'm going to make it be as simple as possible with respect to this Morse function on S4. So there's a minimum, a maximum, and then no other critical points of S4. All the cross sections are just S3. So my projective plane is going to be sitting here, and it'll have a Morse function on it from the height function. And it definitely has to have a minimum, and it has to have a maximum. This is a compact surface. And its Euler characteristic is 1, so it would have to have an index 1 point. And if I could arrange for that to happen, that would be the smallest possible projective plane. Okay? So we can arrange for that to happen. So here are cross sections. So I have a minimum where there's just a single point of tangency with that cross section. And right above it, I have my surface. Cross sections are just small circles, small unknots. And as the height increases, those unknots might move around in the three-dimensional cross sections. Like maybe I'll do a Reidemeister 1 move. Okay, that's perfectly good isotopy. And then maybe these two arcs inside of this unknot get really close together and then are tangent. So those 2 points got really close together and then fused. So this is, I'm drawing for you what does an index 1 point look like in a surface. I have and then 2 horizontal arcs. We all took calculus 3. That's all the like saddle thing. Okay. So now when I go above this height, I should see the opposite resolution, which happens to also be an unknot. So we can have this shrink and eventually a maximum. Okay, so this is very explicitly a projective plane inside of S4. And if I wanted to think about this as a banded unlink with the very end of yesterday, well, I said, what do? You draw an unlink that corresponds to all the minima of the surface, and there's only one. So just the best unlink is the unknot. And then we have a band that corresponds to each one of the index 1 critical points of the surface, and there's only one. So I need to draw a band that corresponds to this, and so that would be something like this. So this is a band that's telling me what happens to my unknot as I go into the future. Yeah?
So for someone who doesn't think about knots, and I'm repeating myself, but is this equivalent to my notion that it's, if you have some nothing isotopy, you know, that with the nothing isotopy for the surface gives you this sort of map from the body?
Well, when we talk about unknotting isotopy, what?
Well, I mean, so for me, when I think about knots, how do I know that a knot in 3 spaces is a knot? You can knot it with your hands, but this really corresponds to a sequence of knots if you think of them over time, that you move it around in a continuous manner without breaking or you know.
Yeah, so I'm defining, that's right, and I'm going to define like 1 or 2 RP2s that are the unknot, and then I would say everything else is unknotted if it's isotopic in space to the one that I'm specifying right now, which agrees with what you're saying, like a classical knot is the unknot if I can move it around in space and turn it into the standard model.
Right.
Okay. All right, so this is almost the best that I can do. Okay. Except I did make a choice here, which is that I said do a Reidemeister 1 move, and there are 2 Reidemeister 1 moves, and they're very different from each other. So I could have changed this crossing, and it would have like also still given me a projective plane, and those are not isotopic in S4. So I also have a projective plane that looks like this. Okay, and I can check. Is this really a surface? Well, I drew an unknot. I drew some band attached to it. And if I do surgery along my band, just like the other day, so I take my unknot and then delete where it meets the band and replace with the rest of the band, then I really do get an unknot. So this really is a surface, and it's describing a surface with 1 min, 1 max, 1 saddle. It's a projective plane. Okay, so these are the 2 like smallest things that you can do. And they are called, which order do I think it is? Which order? I think this one is P+, and this one is P-, maybe? I don't know. The difference between them is if we look at their normal bundle in space, it's a disk bundle over the projective plane. There's more than one of those. So one of these guys has positive Euler number, and one of them has negative Euler number. So they're really not the same in this one. Okay. Okay, so that is my non-trivial example, except it is trivial because it's the unknot, but it's a confusing unknot. So I define these to be the unknots. And then in general, a non-orientable surface is unknotted if it is a connected sum of some number of P pluses and some number of P minuses. Okay, so as the non-orientable genus goes up, there's actually a lot of distinct unknots that are all distinguished by their the Euler bundle, the Euler number of their normal bundle, but it's still a finite number, so it's not that bad. Okay, great. So now I want to tell you some open problems, and there was a reason that I actually did all that spin stuff. So this is my favorite problem. That's not true. This is a problem that I really like, and it's not dimension specific, which I sort of promised yesterday. I want to leave this, but maybe not this. So here's a question that the first time I heard this, I could not believe this was not known, but it's not. So question, knotted two-sphere. And the other sum end is either P plus or P minus. So the question is, given a projective plane, is like all of the knottedness in like a two-sphere part, and the fact that it's a projective plane kind of like just like a coincidence, and I can always pull it off. And we don't know the answer to this question smoothly or topologically locally flat. Which is like, how could that possibly be true, right? So the conjecture that the answer is yes is called the Kinoshita conjecture. Kinoshita wrote several papers studying RP2s that had this property in various four manifolds. I don't think he actually conjectured that this is true. I mean, he didn't write that, so it seems a little bit unfair to like, it's more like Kinoshita's question. So I think it's probably not true. So if you prove that it's true, call it the conjecture. But if you prove that it's wrong, just he asked it, you know. That's not true.
Wait, one is the theorem, the other one is the conjecture.
Well, and Tom conjecture still. Okay.
Is the question known for other types of surfaces besides P2?
Yes, sort of. I can, for positive genus surfaces, there are some results, but like maybe there's some errors in those results, and I'm not sure exactly what the best possible result is. I believe that it is known to be false for Klein bottles, so that answers that. I can actually cite a very old result-ish, that I think is very interesting without adding genus. So, interesting fact is a theorem of Yoshikawa from 1994. He found a link of two projective planes, two RP2s in S4 that can't split as a summand. So you can't find a ball that meets this link in either component in a trivial RP2. This is, again, category independent, like his obstruction works topologically, and the link is smoothly embedded. And the obstruction is very simple. So he had this observation that if you have a projective plane that splits like this, we can say a lot about the fundamental group. So if F admits a projective plane, summand, then when I look at the meridian of F, this is two torsion in the complement of F. And that's true because well, I can figure out what is the fundamental group of the complement of just P plus or minus. They're so small, they each have one minimum. If you've read Dipschitz chapter 6, then you know the Handel decomposition of a complement of a surface. But if you haven't, that's okay. This complement, I can find a cell decomposition where there's a single one cell. So it's going to be a cyclic group. And then I don't have to worry about all the others. I know the homology of the complement from like Alexander duality, and that tells me the group is C mod 2Z. So because I'm connecting something, summing something with group C mod 2Z, like the meridian is two torsion here, all the meridians are conjugate to each other, just like classical knots, they're all two torsion. That's weird. But for his surface, I mean, he just like wrote down a presentation of the fundamental group of this link complement, and like very immediately, both of the meridians of this guy are order 4 in the complement, like because they were just standard elements in a quaternion group, so he didn't even have to like do anything hard. The hard part of this, like the reason that like this happened, is that Yoshikawa is writing the only paper I know of where he was attempting to enumerate surfaces of four manifolds. Like, you know how there's notinfo.org? I own the domain name tonotinfo.org, and I'm just waiting. So the problem is that notinfo.org, by default, I think shows 25 knots on one page, and Yoshikawa's table had 24 surfaces, so it's just like a little bit sad. So very, very small table. The smallest, like 24 surfaces under some notion of small, most of which were not connected, only 6 of which were two spheres, including the unknot. The 6 two spheres here are like the spun trefoil, the 2-twist spun trefoil, the 3-twist spun trefoil, the spun figure 8 knot, the 2-twist spun figure 8 knot. So you know all of those. And then like the very first link of projected planes just had this property. So if you just look for examples, they'll probably prove something. Okay? But I don't know how to approach this. I have no idea if the strategy could possibly work for projected planes or not. But I think it's like a really interesting problem that I don't believe could possibly be true. Possibly yes. Okay, what else? Now I'll tell you my actual favorite problem, which I think is also unbelievable. Okay. And so first I have to tell you a theorem that I didn't believe the first time I heard it, which is a theorem of Kerber from the 1970s, that every S2 in S4 bounds a 3-ball into B5. And specifically, if we're working topological category, a locally flat 3-ball. And the smooth category, it's a smooth 3-ball, not some like weird cone thing. They're all slice. And like, you know, I think a lot of people think about classical knots, think about concordance of knots. The average knot in S3 is not slice, right? They don't bound discs in the 4-ball. That's very special. It's like pretty hard to prove that knots don't bound discs sometimes. And here it's just like every 2-sphere is sliced into B5. And it's like, that never happens. Like usually, if something is like hard in dimension 3, it's impossible in dimension 4. So this is like the one time it's like, yeah, we got them, you know? And I love the proof of this theorem. Not that I've ever read the paper, it's in French, but Nathan Smitkin has, in the paper that he was talking about before, he has a really nice outline and generalization of this proof. And so I would read that before I read the Kerber paper, which is in French. And in fact, there isn't a category problem here at all. Paper from last year, Dar and Powell, they show that if you have a smooth 2-sphere, so if K is a smooth S2 in S4, and it's just topologically sliced, so locally flat, B3 and B5, then K is also smoothly sliced. Smooth in B5. Okay, so I have to say the boundary is smooth in the first place, or else that wouldn't make sense. But if we're looking at smooth 2-spheres in S4, I don't need to like consider the difference between topologically and smoothly sliced. They're just like the same. In fact, I guess I'm saying this in a weird way, because I already know this bounce. Sorry, I should say something like a smooth S2 in any 4 manifold, which is the boundary of a 5 manifold, where pi1 of x is equal to 1. Sorry, that's what I should have said. If I have any simply connected 4 manifolds which bounds, and I have a 2-sphere that bounds a locally flat ball, then I can like just perturb the ball a little bit and make it smooth. That's what I should have said before, because otherwise that was kind of like a trivial statement, and this actually is interesting. But I mean in general, there's not like a weird category dependence on concordance and concordism in this dimension. Okay? But here's something that is open, which is shocking. Well, as much as like this theorem is shocking, but given that now you believe that this is true, it's shocking that we don't know the answer to this. Question, is every length of S2s in S4 size? Okay. And by a length being sliced, I mean the boundary of a disjoint union of 3 balls in B5. Okay. We don't know the answer to this. We know from the Dar and Powell paper that there isn't like a weird category thing here. If you have a smooth length of spheres, it's either sliced or it's not. But somehow we don't know the answer to this. And I don't even have like a proposed counterexample. Every time I like confidently have a proposed counterexample, Hanna-Schwartz proves that it's slice. And so I did write a paper with Michael Klug a few years ago, where we showed that if you could do a different construction, if you could show that there exist two spheres in a different form manifold, S1 cross B3, that satisfies some property about a certain covariant, which I will not define, but I'll tell you sort of what it is. This is Crevera-Milnor, not Klug-Miller. We're not crazy. The Crevera-Milnor invariant needs to be non-zero. And this is something that's valued in the first homology of the ambient manifold with Z-mod 2 coefficients. So it's either 0 or 1. If you just had one pair of two spheres where it's not 0, then the answer is no. And in an earlier paper, we produced lots of two spheres in slightly different form manifold that do have non-trivial Crevera-Milnor invariant, but I don't know how to do it in S1 cross B3. So I think this, for me, this is very interesting. The problem with saying this is a question is you don't know what the Crevera-Milnor invariant is, and you won't answer this either. All I'll do is say that this invariant is measuring something about in a form manifold. I've considered two homotopic spheres, S0 and S1. S0 and S1. And since they're homotopic, like what Dave talked about yesterday, I can relate them by some one parameter family of like finger moves and Whitney moves. Like this is going to trace out an immersed S2 cross I from left to right inside of X4 cross I. So I have some immersed 3 manifold. It intersects itself in curves, which means now I'm back in a really comfortable setting because I have a link in a 3 manifold. I'm like, we all like that way better, right? So what I'm really doing is I am measure something, linking information about this link. This is defined in the 1990s by Spun, having to do with frequency and stuff. Okay. So I think the sliceness is like a super interesting question, and I have nothing interesting to say about it other than that, because I don't have any ideas. Last open problem, which I do have something interesting to say about, and this is a very well-known problem. I think, on average, if I were talking to people who study surfaces, and I said, open problem in S4, this is the one that they would expect. Which I'll phrase as like a problem and a subproblem. So question, do there exist exotic surfaces? In S4. Okay, and by exotic, I mean, can you find a pair of surfaces that are topologically isotopic, but not smoothly isotopic? And it's not a very good question, because the answer is yes. Yes, but so far, all the examples are non-orientable. And non-orientable in a very crucial way in the proof. So we still don't know if there exist exotic pairs of orientable surfaces in S4. And if you had an example of two oriented surfaces, even like genus 100, it doesn't matter, that would be like a big deal. I don't have any idea how to deal with the orientedness, but I want to tell you about these non-orientable examples. They've existed in the literature for a long time. So these non-orientable examples, remember we heard about the cross-cap number yesterday? A non-orientable surface has like a genus, connected sum of some number of RP2s. So for cross-cap number 10, the first examples, finishing crack on 0 back in the 80s. And at this time they had to do two really hard things. They had to construct surfaces and prove that they were topologically isotopic. That's pretty hard. And then they had to prove that they weren't smoothly isotopic, which is hard, but honestly I think the first part's harder. And then Finishin simplified this a little bit many years later to cross-cap number 6. And then last December, there was a paper for cross-cap number 5. And I'll explain why this is an anomaly by this paper by Jin Miyazawa. Okay, so the reason that this is an anomaly is that all of these surfaces, not only are they making exotic pairs, they're making something even better than that, which is exotic unknots. All of the surfaces that they're constructed in these papers are topologically isotopic to an unknotted surface, but not smoothly isotopic to an unknotted surface. Okay? And in this k equals 10 case, the unknot that they're topologically isotopic to is p minus connect some 9p plus. So remember, an unknot is a connect sum of minus some positive projected planes. So this is an unknot. It's one of the valid unknots across number 10. And for k equals 6, it was p minus connect sum of 5p plus. And for k equals 5, it was p minus connect sum of 4p plus. And all three of these papers that I've just written in red, the way that they distinguished these surfaces is to look at their double branch covers. In all cases, the double branch covers of the surfaces that they consider are diffeomorphic four manifolds. They're homomorphic four manifolds, but not diffeomorphic. That's the abstraction. And the reason that they're not diffeomorphic, in these first two cases, it's Seiberg-Witten invariance. I mean, this one is too, but it just works differently. And they sort of work backwards, where they actually started off with four manifolds that they knew weren't diffeomorphic, like exotic pairs, and they happened to know that those four manifolds emitted an involution from the way that they were constructed, and they took the quotient and proved they got S4. So it's all just working backwards. Like they started off with the obstruction and then got the examples. Okay. This Miyazawa paper is fundamentally different. He's making examples of P minus topologically, which is, it's scary because it's definite. Like all these other surfaces include a P minus summand and a P plus summand, and that tells us that their double branch covers are indefinite four manifolds. So if you don't think about four manifolds, then this means nothing, like you don't care about that. But if you do think about four manifolds, it's like that helps, right? The reason that this is scary for P minus is that I'll just tell you what is the double branch cover of S4 with branch set P minus. It's CP2. So if he were going to use this strategy, he would need to produce a four manifold that's homomorphic to CP2, but not diffeomorphic to CP2. And if he did that, I would have led off with that, right? That would be crazy. So he didn't do that. Instead, he did something that is still a very classical idea, but he needed to invent a lot of new technology to carry it out. And the classical idea is what Malcolm talked about, which is just add an involution everywhere, and then use something with that. So here, we draw a schematic of what's going on. We have S4. That's S4, that's what it looks like. And inside of S4, we have two surfaces. One is P minus, and the other is some other projected plane, F. Okay? And now I have double branch covers that branch over these two branch surfaces. And I'll get two four manifolds. In the first case, it's CP2. And in the second case, it's just some four manifold X. But not only is it a manifold, it's a covering space. So it's a manifold that has an involution on it, because it's a twofold covering space. Here I have an involution that just exchanges any 2 points that have the same image downstairs. And again, because I understand this projected plane very explicitly, I can actually figure out what this involution is, and it's the only one that I think you could have possibly guessed, which is its complex conjugation. And Evan could move on. Okay, so this is complex conjugation. And this is just some other involution over here that comes from this covering action. And so what Miyazawa actually did was prove like the equivariant version of what happened to these papers. He showed that CP2, that's just fine. CP2 Okay. And it's not obvious from this paper whether the failure for these to be diffeomorphic is at the manifold level or at the involution level. And he doesn't know in the paper. Okay. We do know the answer now, but let me tell you what F is. Like I just said, oh, F is some mysterious projective plane, and it's not. Like this is the other unbelievable part. How could this be the example? So the reason I spent so long talking about roll spun and twist spun knots is F, Miyazawa. F is a projective plane that is obtained as a connected sum of a knotted two-sphere with P minus, which is consistent with the Kaneshita conjecture that I talked about before, so I don't have a potential counterexample to that. And the knotted two-sphere is a zero twist, one roll spin of a specific classical knot, J, where J is the pretzel knot minus 2, 3, 7. You know, that. Okay. Just like, I mean, I want to clarify, this is a really great paper, right? That's so dumb. The fact that this is topologically unknotted, isotopic to the unknot topologically, is not something that Miyazawa has to prove. It's actually a consequence of an older paper in 1970s by Lawson. All Miyazawa had to do was compute the fundamental group of this complement and see that it was the same as the unknotted complement, and that would tell him immediately they're topologically isotopic. So all the content of this paper is thinking of the example and then doing this computation, like, well, defining a smooth invariant, which is he's measuring how many solutions there are to the Tybor-Putin equations that are fixed by a certain evolution. And that's hard to count, right? So he has to do something like pretty hard in this paper. And it's really specific to having an evolution. So the theorem, like this is what I was working on this semester. And this is much easier to prove, but I also don't have to because there's like 5 minutes left tops at this top. Perfect. 3 minutes left at this top. 2, ideal. So I wrote this theorem with Mark Hughes and Sung-Won Kim because we just don't have any independence. How many papers do I have with Sung-Won? I have like 7 papers with Sung-Won, and Mark and Sung-Won and I have like 5 papers as a group, and we're writing 2 more right now. It's very fun. 2024. This is going to look unrelated. Okay. We proved that the double branch cover of a M twist N spun knot is diffeomorphic to the double branch cover of if I add 4 twists. And if you're willing to add an unknotted RP2, oops, plus 4, thank you. Different M. This is connect sum P plus or minus. It's diffeomorphic to the double branch cover if I add 2 twists. Which Bob Gom sent me an email right afterwards, commenting on how he liked that like the change from 4 to 2 is because CP2 isn't spin, and I was like, what a great comment. Yes. So just think about that. Okay, and we use this like excellent fact of whatever it is, Van and Stern. This knot is like a magic knot. It shows up in every paper, and in particular, it showed up in Van and Stern's paper on how to construct lens spaces in like the 1980s or whatever, where they observed that a certain Dane surgery is a lens space. It's the 18.5. Why would that possibly be related? I told you that roll twist spin knots, as long as you twist a non-zero number of times, are fibered, and the fiber was obtained by Dane surgery on the knot and some kind of branch cover. I'm not going to write the formula again, so just trust me that if I take the 18 twist, 1 roll spin of J, it's fibered, and the fiber is punctured the 18-fold cover of the lens space 18 and 5. Okay, so what's that? You know, it's an 18-fold lens space, so the fundamental group is Z mod 18, and I took an 18-fold cover, so I got S3. Great. And it's punctured, so it's B3. So this is the unknot. And that's also dumb. But yeah, so this is the unknot. And so we immediately look at our formula and see, well, okay, so I'm allowed to add an even number of twists when I have a P plus. So that means that this double branch cover of this guy is the same as the double branch cover of 18 twist, 1 roll, connect some P minus, which is the unknot connect some P minus, which is P minus. So they have the same double branch cover. But the really annoying thing is that 18 is 2 mod 4. So the remaining open question, so open, it's a consequence of all of this that the double branch cover of just the 2-sphere part, tau 0 rho 18 of J, is a homotopy 4-sphere. It's homeomorphic to S4. Is it diffeomorphic to S4? This specifically doesn't work, so I have no idea. And this is my favorite homotopy 4-sphere right now because it's such a huge coincidence that this works. Somebody pointed out to me that every other family of homotopy 4-spheres are a family right now. I mean, anything I can think of with the construction of a homotopy 4-sphere, it probably has a lot of parameters, and you can vary them and just get an infinite number of potential counterexamples, which means that's not going to work. That's too hard. But this is very specific to this particular pretzel knot. This pretzel knot, I went to lens space surgery, and somehow that shows up in here. And this pretzel knot, well, it is a pretzel knot with a certain determinant, and that shows up in here. And it's I don't know, Miyazawa, which knots he could have possibly used in this paper, but it's not a coincidence that it's this one. So yeah, now I'm out of time, and I'll leave you with that. Prove that, please.
Are there questions?
Okay,
Yeah, great.
maybe you answered this in one fashion. When you change M and N, do you know that you always get different knots?
Not necessarily because, well, in this case, M and N give me the unknot. But in fact, it's a theorem of Zebon, and I didn't say this.
Oh.
It follows from a statement that if I twist once and don't roll, I also get the unknot. So there's two different parameters that give me the unknot. But we do understand when this happens, especially if we don't roll, if we twist. There's this nice paper by Tara Gaito has a paper from the 1990s, sort of measuring when this happens.
Are there characterizations of how M and N look and whether the two knots you get are the same?
Yeah, I think there's a characterization that it's Tara Gaito wrote something complicated about the knot fundamental group, looking at taking certain quotients of the knot group and then looking at orders of certain elements in those quotients. But I don't remember the exact statement, but I do think we know.
Okay.
That's a good question. Yeah, Evan.
Do any of the techniques of Miyazawa tell you that this homotopy 4-sphere is not equivariantly diffeomorphic to the usual 4-sphere and its usual involution around it?
So the weird thing is that even though the projective plane that I'm looking at is topologically unknotted, the 2-sphere, this particular roll spin is not topologically unknotted. That's right. I mean, it is really big, non-trivial, non-Z fundamental group in its complement. It just happens to become cyclic when I add one relation, which is what this P minus does. So the involution, it's certainly not topologically equivalent to the standard one, but Miyazawa does have some comments about either this is an exotic S4, or it's a standard S4, and there are involutions on S4 that don't preserve any positive scalar curvature metric or something like that. Just standard time.